All right, so let's go on, do the next data point, where 20 milliliters of sodium hydroxide have been added. Go through the whole thing again. We have 0.004 moles of HOCl and 0.002 this time moles of hydroxide. Yes? You all right back there? Nice. That goes to 0, that goes down to 0.002 mole. Hydroxide, again, was the limiting reagent. The OCl goes from 0 up to 0.002.
So we
Huh?
change the concentration or log.
Yes. Yes, it is. Now, once again, I have this ice table set up, but we don't need it because we still have a buffer. And it's going to look like this. The pH equals, the pKa is the same every time. So once we found that 7.46, we just stick with it. Plus the log, oh, what's happening here? Log of 0.002 divided by 0.002. I just squeezed it in there. Hopefully you know what that is. So in this case, yes, this term right here, log of a ratio of 1, gives you 0. So that the pH of this data point is 7.46. Now let's make a couple of observations about this data point. Where are we in the titration at this data point? Look at the amount of HOCl that we started with and how much we have now. We're halfway to the equivalence point. The equivalence point is where we added just enough hydroxide to neutralize all that, yes? We're halfway there. So what do you know? We're going to call this point in the titration the halfway point. It's a pretty big deal, really. Because what else do you notice about the halfway point?
It's not a 7.
It's not 7. Yeah, the pH. And it's actually basic. The halfway point pH is basic. Is it always every time? No. It's only basic because this was such a weak base. And we'll talk about that a little bit more later. No, actually, I guess I could mention that now. When you have the same amount of HOCl and its conjugate base, if you have a basic pH for that solution, what does that mean about the strengths of these two things? This is a stronger base than that is as an acid, yeah. Look at the Ka value. If we found Kb of that, it would be bigger than that number. Because they multiply together to give 10 to the negative 14. Yes? So yeah, that is a stronger base. Another thing I want you to notice about this is, at the halfway point, notice what happens to the ratio of the base to acid. Would that happen every time at the halfway point?
Yeah.
Yes, it would. So that means at the halfway point, the pH equals the pKa of the acid. Every time. That's cool. And you're going to like knowing that. I have the whole next slide dedicated to that. I don't think it's necessary to write every word of this. Just write at the halfway point, pH equals pKa. That really is all you need.
Just for weak acids?
Yeah, only when you're with the weak acid, yes. Because we would never use the buffer equation for a strong titration, because there's never a buffer present. A buffer's got to be a weak acid and its conjugate base. So again, don't write down everything because this is all just review. Just write down at the halfway point, the pH of the solution at that point is equal to the pKa of the acid. Yeah.
You always go up by 10 milliliters.
No, when we actually do the lab, we'll go up by like 1 or 2. So yeah, you'll have a lot of data points when you actually do it. But then you just put it into Excel and you have Excel graphic for you. It's not like you got to do
Is
it all.
that the same for a weak base and a
Yes, it is the same for a weak base, and we'll see this because we'll do a weak base titration. When you are at the halfway point of a weak base titration, the pH is equal to the pKa of the conjugate acid. It's not of the base that you're titrating, it's of its conjugate acid.
Okay.
And we'll see that. Yeah, because it's always Ka. Even if you're titrating a base, you still use the Ka of the conjugate acid. Matt?
So we use halfway point, meaning that half of the H plus concentration, right?
Yes.
So
The half the moles of the H plus. Yeah.
So is it every time that at the halfway point the H plus concentration and the base concentration is always going to be the same?
Yes. It's only at that point.
Okay.
It only happens at that point. And only for a week. Yeah. Next week, when we do a lab, we have a lab that actually will have several different things that you have to do. One of the parts of the lab is where I'm going to give you an unknown acid. And I'm going to ask you to determine what the Ka of that acid is without knowing what it is. It's going to be very useful to know that. You can do the titration at the halfway point of the titration. That's equal to the pK. The pH is equal to the pKa of the acid. You can figure out what acid it is from that. So it's going to be real good to know that. And there's going to be other problems where you'll need that halfway point data for it. Okay, now let's keep going on. Now we're getting closer to the actual equivalence point. We've gone now past the halfway point, so we're at 0.004 moles for HOCl. It's the same every time. Hydroxide, now we've added 30 ml, which gives us 0.003 moles. And initially there was 0 of that. Still our limiting reagent is the hydroxide, so that goes to 0, and the HOCl goes to 0.001 moles. This OCl goes to 0.003 moles. Now we're at the point we have more OCl than we have HOCl, and OCl is stronger. So I could see the pH continuing to go up by quite a bit. We're not at the equivalence point. It really jumps at the equivalence point, but we'll just keep going from there. Now I have the ice table set up, but once again, for this last time, we can still use the buffer equation because we still have some acid and its conjugate base present. As long as both are there, use the buffer equation. So we have pH equals pKa 7.46 plus the log, this time now of 0.003 divided by 0.001. And you get what? 7.93?
This is past the equivalence.
Mm-hmm. No, I'm sorry. No, it's not. It's past the halfway point. It's not yet. It's not the equivalence point because at the equivalence point, the HOCl, the original acid, would have to run out.
I thought the equivalence point was when they were both neutralized.
Yes, and that's not happening yet. We still have a limiting reagent of this one. When both of them run out at the same time, that's the equivalence point.
So there's a difference between halfway point and equivalence.
Oh yeah, the halfway point is halfway to the equivalence point. It's going to wind up taking 40 milliliters of the base to get to the equivalence point. So half of that was at the 20 milliliter point. Okay, well, our time with the buffer equation is now over, and we'll have to do equilibrium in the next data point because we're now at the equivalence point where we have 40 milliliters of sodium hydroxide added with 0.004 moles of that, 0.004 moles of that, and 0 of that. So now in this case, both these run out to 0. That OCl goes up to 0.004 moles. Is this a neutral solution? We're at the equivalence point. We have neutralized all of the original acid. There's no acid present there. There's no base present there. Is it neutral? No, it's not. Why? Because there's still this weak base. Now, the conjugate base is still present, making this a basic solution. So at the equivalence point, when you have a strong a strong base titration, you get 7 every time for the equivalence point pH. When you have a weak acid titration, you're always going to have, at the equivalence point, there's going to be some of its conjugate base there. So it's not going to be neutral. So we have to figure out what the pH is from that conjugate base. That's why I now have set up this ice table at the bottom. And there's no shortcut for this one. We have to do the equilibrium. So we have a solution in which we have a weak base, and that's all that's in this solution to dictate what the pH is. So the job of a base is to take a hydrogen. There's no anything there except for water, so it's going to take a hydrogen from water molecules. That's what our chemical equation is. I warned you that one of the hardest things, probably the hardest thing in this chapter, is knowing what chemical equation to write. You have to recognize this is a base, and then it's going to react with water. Just like there's a chapter 14 problem. Now, that base is going to take a hydrogen off of water, make OH, and then the HOCl. And that production of OH is what makes this thing a base. Stretching, or you got a question? Okay, so I have the ice table set up. This is what we have to do. Now remember, when we do the ice table, we have to use molarity, not moles, because we're dealing with a K value, and K is always the ratio of the molarities. All right, so the concentration, 0.004 moles over the total volume, which is 80 ml, 0.08 liters. 0.004 divided by 0.08. That's how much OCl we have. How much HOCl are we starting with?
0.
0, because it all ran out. It just got neutralized. So initially, that 0 and that is all we have to dictate the pH. So that's 0.05 molarity. So in equilibrium, that's going to go 0.05 minus X. It's going to shift to the right to make some of these products. That's X and that's X.
What's the molarity?
It's 0.05. It's 0.004. That's the moles divided by the liters, which is 40 plus 40 milliliters. So it's 0.08 on the bottom for 80 milliliters. Okay, you see all that? So let's find what the pH of this thing is. Now this is going to take several steps. We're going to do Kb, because this is a base. Well, we know the Ka of HOCl, so we have to find the Kb. That's going to be Kw divided by the Ka. And that's going to be equal to x squared over 0.05 minus x. So neglect that minus x term and solve for x. That's going to give us the hydroxide concentration. Take the negative log to get POH and then subtract from 14. There's a lot of steps there. Well, Kb is Kw divided by Ka. And we know what the Ka is from up there. So when you get that Kb value, set it equal to x squared over 0.05 minus x. You're missing something? Well, remember this. Any acid times its conjugate base, Ka times Kb equals Kw. That's where I'm getting that. Yeah. So can you calculate that and come up with a pH of the solution?
So do we still have a buffer? No?
It's no longer a buffer because there was no weak acid there.
It has a weak base now.
Yeah, but you need both there for a buffer. So it's just a weak base solution right now.
Okay.
So we can't use.
It's a bummer, I know. It makes it harder.
We can't use 5% molarity.
Oh yeah, you can, because this Kb is small. It's very small.
Yeah. Okay. Good.
It's like 10 to the negative 6th or 5th, something like that. It's small enough. Anybody have a pH for this thing? 10.08? Okay, make sure you can calculate down to that. Don't just take everybody's word for it. So remember, this is the data point that's at the equivalence point.